Hi Cougars! In this video I'm going to go over the super important points in chapter 6, and this video is meant to supplement the lecture videos that are already on Blackboard. So if you haven't watched those yet, go back and watch those before you watch this. Otherwise this isn't going to make a ton of sense. I'm not going to go over every little detail. I'm just going to point out some things in a way that I think might be helpful. So valence electrons, remember, are those electrons in the outermost shell. They participate in bonding. They help determine or predict behavior of certain elements. And I'm just going to label the periodic table here with valence electrons. And so everything in group 1 has 1. Everything in group 2 has 2. We skip all these because they can vary. I'll talk more about that in a minute. 3, 4, 5, 6, 7, 8. Now there's an exception here. In group 18, helium only has 2 electrons, period, so it cannot have 8 valence electrons. Now, everything wants to follow the octet rule. The octet rule is 8 electrons in the outer shell. It makes it more stable. So in order to do that, elements are going to, again, gain or lose electrons. And when they gain or lose electrons, they have a charge. And we can predict the charge that they're going to have based on how many electrons they have to gain or lose. So I'm going to fill that in as well. Plus 1, plus 2, plus 3, plus or minus 4, minus 3, minus 2, minus 1, 0. All right, it makes sense that everything in group 18 doesn't have a charge. The ionic charge is 0 because it's all stable. It's all following the octet rule. It doesn't need to gain or lose any electrons. But everything in group 1 has 1 valence electron. It's easier to lose that 1 electron than to gain 7 more to get to 8. So when something in group 1 forms an ion, it's going to be a +1 ion because it's going to lose 1 electron. It's going to lose 1 negative and therefore be positive. Everything in group 17 here has 7 valence electrons. It only needs 1 more. So it's going to gain 1, therefore gain an electron, gain a negative charge, so it'll have a -1 charge. Okay. Next, ionic bonds. Those are formed between metals, which are these guys, and nonmetals, which are these guys, plus hydrogen. And I'm not going to get too far into what happens with the electrons. We know that electrons are transferred in ionic bonds, but what I want to show you here is the naming and the formula writing. So for sodium, if I come over here and look at sodium's in group 1, that means it's going to have a +1 charge. +1. Chlorine is in group 17. It's going to have a -1 charge. -1. The +1 and -1 cancel. Therefore, the formula is just NaCl. Okay? And what this means is that sodium gives its 1 valence electron that it doesn't want to chlorine to satisfy its octet. So now they're bonded because sodium transferred its electron to chlorine, and now it's overall a neutral compound, meaning there's no overall charge. The +1, -1 cancel. Again, this is a metal and a nonmetal. Okay. Whoops, I did not mean to do that. All right, that's better. And then what I want to do is talk about aluminum bromide. Let's bring him up here. And this is a little bit different. So last time I gave you the formula, NaCl. Na is sodium, chlorine is chloride. Change the ending to "ide." That's how you name it. Now I'm giving you the name first, and we're going to write the formula. So, let me erase that. Aluminum, we see here In group 13, it has a +3 charge, so Al +3. And then bromine is here in group 17. It has a -1 charge. Bromine, -1. Now there's a couple ways you can do this. To me, the easiest way is to just crisscross those numbers. Crisscross the charges, meaning Al3, AlBr3. So this 3 came down here, and this 1 would be here, but we don't have to write a subscript of 1. Now, if you're thinking like, why that, I don't understand why that's the case. Here's why. Let's say what's happening here? Go away. Delete. Sorry. Let's say you see that we have aluminum with a +3 charge, bromine with a -1 charge. In order for that to be neutral, we know we need 2 more bromines with that -1 charge. So now I have +3 and then -1, -1, -1, which is -3. And so that altogether would be neutral. And the way we would denote that there are 3 bromines is by writing a little subscript of 3. Okay. Moving on. Now remember earlier I said let's go ahead and just skip this middle block because the the ionic charge can vary. These are called the transition metals. The ionic charge can vary, and therefore it has to be identified with a Roman numeral. So here the example I'm showing you is iron 3 chloride. This is Roman numeral 3. So you would come to the periodic table and you say, all right, iron, that's Fe. And you see that Roman numeral here, that tells you the charge of iron, +3. All right, and then chlorine is here. We know that's -1, Cl -1. And I just would crisscross those numbers so it becomes FeCl3. All right. How do you know it's positive? Because it comes first. All ionic bonds are metal first, non-metal second. It's always cation first, anion second. The positive charge always comes first, so you know it's going to be positive. Now, let's say I gave you CuCl2 and I said, what's the name of this formula? So before I gave you the name and asked for the formula, which is FeCl3, now I'm giving you the formula and asking you the name. So you would look for Cu, that's here. You know that's copper. And then chlorine, we know is chloride. But because copper is a transition metal, I need to identify the charge with a Roman numeral. How do I know the charge? I have to go back and look at the formula. So just as we crisscross these here, we're going to uncross them here. We know the charge of chlorine is -1. It's in group 17. But copper, I have to identify that using this subscript here. Like that. So we know that copper has a +2 charge, so I have to identify that with a Roman numeral 2. Okay. Next. What about the polyatomic ions? So again, I just want to make sure that you understand that when you're naming these compounds, you are never going to change the names of these. And these charges are also set in stone. You can't change it. So let's say I give you this formula or this name here, magnesium nitrate, and I ask you for the formula. Well, you're going to go to your periodic table, find magnesium. It's Mg. And we know it's in group 2, which means, so here's group 2, here's magnesium, which means it has a +2 charge. So I'm going to go ahead and give magnesium a +2 charge. And then nitrate. So here's the big mistake students make. They see nitrate and they're like, oh, that's nitrogen. It's not. It would be nitride if it was just nitrogen by itself. Because it's nitrate, you have to when you see that name, you have to recognize like, oh, that's a polyatomic ion. I need to go look up what that is. NO3 with a -1 charge. Whoa, what happened? NO3 -1 charge. Okay, so a polyatomic ion is an ion with many atoms. Poly means many, atomic atom, many atoms. So I want you to think of NO3 with a -1 charge as a little package. You can't break it apart. You cannot change the name. So same as before, you're going to crisscross those charges. And this becomes MgNO3 2. Now, how did I know to write the parentheses? Well, I need to show that I have 2 nitrates, so 2 -1 charges to balance the +1. All right, so that is the formula there. Next. All of that was for ionic bonding. Now I want to talk very briefly about covalent molecular bonding or molecular compounds. So my suggestion is to try to memorize these prefixes here because they're going to just come up all the time and it's easier to just know it without having to look it up. And you're going to be doing a couple things with this information. I'm either going to give you the name like I did here and ask you the formula, or I'm going to give you the formula and ask you the name. For this one, I'm just giving you the name. So I know that di means 2. Okay. So I come down here and I look for boron. Here's boron, so that's a B. And there are 2 of them, B2, okay? And then oxygen is here, I have 3 oxygens, O3, B2O3, that's the formula. Now, the biggest difference between ionic and covalent is covalent or molecular are going to always use these prefixes, and you cannot use mono first. For example, we all know what this is, CO2. What is that called? Carbon dioxide, not monocarbon dioxide. So even if there's only one atom of the first atom present, or the first element present, that's understood. You do not need to use mono first. This is not monocarbon dioxide, it's just carbon dioxide. Okay? Last, this was the section in the book that I was saying, like, don't get too heavily involved in it because you're not going to use a lot of that information. The main thing is that I want you to understand the electronegativity trend, which is that electronegativity increases as you go across a group and decreases as you go down a period. And all these little numbers you see in the periodic table here are electronegativity values. And what you're going to do with those numbers is take the difference in order to calculate if it's nonpolar covalent, polar covalent, or ionic. And this can get a lot deeper, and there's a lot more to this, but this is just like a very surface level understanding that you need to know. So I have 2 examples already listed here. NaCl, so you find sodium, 0.93. You find chlorine, 3.16. Take the difference, and it is going to be absolute value. Take the difference of those, it's 2.23. Come down here, 2.23 would fit here, ionic. Well, guess what? We already knew that because sodium is a metal and chlorine is a nonmetal. So I'm going to write metal plus nonmetal, ionic. We already knew that, okay? And then the next one is NO, which is nitrogen monoxide, not mononitrogen monoxide, but nitrogen monoxide. I come over here to this table, find their electronegativity values. And again, it's absolute value difference, 0.4. Come down here, that's their non-polar covalent bonding. So that's all you need to be able to do. Is I want you to understand the trend of electronegativity, the element's ability to attract electrons, and know what to do with the electronegativity values and how it relates to polarity. All right. And that's it. I hope this helped. Please let me know if you have any questions, and I'll see